All right, then let's go ahead and we're going to talk about the power plant, keeping in mind we have two types of power plants out there. We have the 712 still, and we have the 714. For the active component, all active duty units are now 714s except for this one. And this one is a good majority. I think, last word I got, I think there's 6 714s or 712s out there still. Okay? I don't know where you all are. I know you are going to plan on changing them, but for the most part, you all are still 712s to the best of my knowledge. I don't think you've converted any to 714s yet. But I think you all are getting ready to, so.
We have all 714s.
You're all 714s now. Okay. So, some countries have already transferred over, some have not. So let's go ahead and talk about the 714. The 714 itself originated on the MH version of the CH-47. Keeping in mind that even the MH is not up to the latest and greatest 714 engines. The E's and the G's have the latest and greatest, but some of their MH-47 Echoes still have the Lycoming 714 engines. Okay? And they're in the process of getting rid of them now and transferring over to the GAs. That is the Echo, by the way. Terminal Learning Objective Action. Describe components, operational characteristics, functions, limitations, malfunctions, and emergency procedures of the CH-47D T55 GA-714 Alpha power plant. And for those that are curious, yes, the Bravo's out there. I don't know what the changes are going to be. And I don't know when they're going to start. But I know 2 users conferences ago, they did talk about the 714 Bravo. Conditions in a classroom environment, given a student handout, standards, correctly answer in writing without reference. 11 of 16 questions pertaining to the components, operational characteristics, limitations, functions, malfunctions, and emergency procedures of the CH-47D T55 GA-714 Alpha power plant in accordance with TM 1-1520, 240-10, and the student handouts. Safety requirements, none. Risk assessment, low. Environmental considerations, none. Evaluations, the performance of the TLO will be evaluated in CH-47D Systems Examination 2. The examination and critique are scheduled for 2 hours. Students must obtain a passing score of 70%. The 70% is applicable to the Flight School 21. AQC, it's a go, no-go standard, as you're already familiar with. Any questions about that? Now, class outline. We're going to do the T55 GA-714 Alpha general description. We kind of run that as a pre-flight class. Description of the major sections of the 714, descriptions of the engine subsystems, descriptions of the FADEC, which is what everybody likes to know. And we'll talk more about that FADEC in just a second. FADEC operation, malfunctions, indications, and emergency procedures. LSA 1, list the general descriptions of the power plant. General descriptions. It's a T55 series engines, most of our engines are. It's manufactured by Honeywell, hence the GA. Okay, L was for Lycoming. Honeywell does not have their own designation, so they're going with the GA for right now. Okay, but they are Honeywell engines, and a lot of the components are Honeywell. It's a 714 Alpha. We have 2 engines installed, and the engines themselves are going to drive engine transmissions that are mounted to the front of the engine. Now, I like this slide only in the fact that we're going to hit all the key components off of it, but what I like to point out is under that weight, 832 pounds, as I'm struggling to move this massive engine around, I want you to appreciate that this is my physical fitness for, I'd like to say the year, but we probably do this class 4 or 5 times a year, so that's when I get my PT. So just so you have an appreciation as I'm struggling back there. And all the rest of the stuff will end up being covered as we go along. Now, with this class, we're going to do something very, very unique in the fact that we have to front load all the abbreviations because there's so many of them that instead of hitting them as we go along, we're just going to go ahead and front load them. That way, as we make reference to them, you know what we're talking about. We're going to start off with FADEC, Full Authority Digital Electronic Control. Gentlemen, you know, everybody gets wigged out about this engine and the differences, okay? Reality is, the only thing that this 714 engine does, or gives us the option to do, is it has a computer interaction now. Before it didn't. On 712s, you were its eyes, its ears, its reaction. You were everything for that engine. If you misdiagnosed the problem and reacted wrong, it reacted wrong. The nice thing about the 714 is basically this FADEC is nothing more than a computer control. Contrary to popular belief, it is not a component. It is a system of fuel management is what it is, being controlled by a computer. That's the simple gist of it. And everybody looks for a FADEC component. There's no such thing. It's a system. And we're going to show you all the pieces and parts that make up the FADEC system. The DECU just happens to be one of them, which stands for Digital Electronic Control Unit, a fancy-dancy term for a computer, which means we're going to talk about how many of them. 2. Why 2? 2 engines. Each engine has one. The HMA, Hydromechanical Metering Assembly, which took the place of the fuel control on the engine. And we will actually talk a little bit more in depth about it, but we're not going to complicate it. We didn't make you learn the internal pieces and parts of the old fuel control, and we're not going to do that with this one. We just want you to understand how it interacts with the computer and what it's doing. Now, part of the HMA is the HMU, which is the Hydromechanical Metering Unit, and the FPU, Fuel Pumping Unit. Those 2 pieces and parts make up the HMA. RDPS, Ratio Detector Power Supply. Ratio Detector Power Supply is part of your torque metering system. The ratio detector power supply is part of your torque metering system, is what you're going to find out. Primary, or PRI, stands for primary operation of the FADEC. Basically, in the primary mode, what's controlling those engines?
Computer.
The computer. The computer. Okay, which means now we go into REV, which stands for revisionary, or the backup system of the FADEC. Now what you will find out is they are 2 separate entities in there as far as channels. Keep in mind, just like you, in the 712, part of the reasons why we had the possibility of making mistakes is people didn't cross-reference well enough. Well, guess what this has to do too? This has to cross-reference too. And not only does it need to cross-reference, we need to have a redundancy system so that if one system fails, the other system's still going to be providing the required information for the computer to react. But keep in mind, in revisionary mode, what else happens? Who now takes over control of that engine? You do. You do. CONT, contingency power. Okay, taking the place of the old emergency power, but the result is the same. Contingency power allows us to have the power required to sustain flight on a single engine. That's all contingency power gives us the ability to do. GP, gas producing in one section of your engine. Not general purpose, gas producing, which is nothing new. We always have a gas producing section of an engine. As long as we're talking turbine engines, you're going to have a gas producing section. PT, power turbine, N2 system. Same thing. Nothing new. All turbine engines have an N2 system. Now, PTIT, power turbine inlet temperature. equivalent to TGT, TOT, TET, T, all those fancy dancy terms, depending on what aircraft you come in. The only thing is what determines which one it's going to be is where we're actually taking the measurement of the hot gases. In our case, it's at the power turbine inlet temperature because we're measuring the gases as it comes off the gas producing blades just prior to going onto the power turbine wheels. And based on that, that's why we call it the PTIT. It's measuring the inlet gases just prior to going into the power turbine section of the engine. And then my favorite, the accessory gearbox. Why is it my favorite? Because if you can identify the accessory gearbox 10 out of 10 times, there's nothing you can't learn on this aircraft's engines. Okay? Now, why is that? Because everything on this engine is N1 driven. I'll say that again. Everything on this engine is N1 driven. Why is that important to understand? Some engines, you got some things that are N1 driven, some things that are N2 driven, and then you got some things that are driven by both sections of the engines depending on the requirements. In our case, everything is N1 driven. Now why would we do that? Why would the engineers, Honeywell in this case, Lycoming before that, make everything on this engine N1 driven?
Parasitic power loss.
What?
Parasitic power loss gives everything to the N2 system to drive the transmission.
Okay, fancy dancy term, but he's 100% correct. By making everything N1 driven, everything that the N2 section of this engine has to give is going to be available for doing the job we want it to do, and that's drive the transmission, which is going to drive the rotors. That way we don't have any power loss from our N2 sections because it's driving other pieces and parts. It's that simple, ladies or gentlemen. It's that simple. Now, why would that be important to understand? Because everything's N1 driven, that accessory gearbox is going to make sense. Because we're going to find out a lot of pieces and parts are driven right off of it. Now, as we look at the engine, just like all engines, we're going to break it down into the N1 system and N2 system. In this picture, the N1 system is your blue, which is known as your gas-producing section of your engine. And what you're going to notice is it started with something that you already talked about, which was what? What did you talk about yesterday? That hydraulic starter at the 12 o'clock position, driven off of what system? Utility hydraulic system. It's a hydraulic motor that's going to end up driving this assembly right here, which is going to end up driving the gas producing or the compressor section of the engine, also resulting in the accessory gearbox being driven, which is going to result in the driving of your fuel pump and your oil pump and the FPU portion of the hydromechanical metering assembly as we go along. The N2 system, your power turbine section of your engine, is going to be the red, and what you're going to notice is we got two blue compressor blades. Why? That's what's going to make this engine self-sustaining when we turn off that hydraulic starter. That's what's going to keep the compressor section turning. And then the same hot air gases that are driving that compressor blades are going to drive your power turbine wheels, which is going to result in driving a shaft, which is going to come back out here to the output shaft, to the front of the engine, and drive and be connected to your engine transmission. And then it's going to drive your engine transmission. That's all part of your N2 system. Now, I will point out that you now have a shaft right here, which is going to result in driving something that we never had before, which is an N2 speed sensor. But you'll notice when we talk about the N2 speed sensor, it is not connected to your gauge up in the cockpit. It's strictly for the computer. Okay, it doesn't drive anything up in the cockpit. We still did not add an N2 gauge. And I'll go one step farther. The ability to hook that system in has always been there. We've just never used it. Any questions so far? Now, shaft horsepower of this engine. As you look, 10-minute limit. What do we mean 10-minute limit? Based on what? PTIT. Keep that in mind. PTIT, 900 degrees C. We have a shaft horsepower of 4,867 shaft horsepower. Now that's easy to say, but let's make sure that everybody understands. What is the difference? That used to be 3,750 shaft horsepower on the 712. Okay, does that tell you what type of shaft horsepower we're now getting out of these 714 engines? And by the time we're done, you're going to understand what they improved to increase that shaft horsepower. 2.5, what are we talking about? What is it? 930, also known as contingency power. That's when you're in contingency power. You got 5069 shaft horsepower. Just so you can appreciate it, just like we did before, the 712 was 4,500. 4,500. So now you'll notice that just under the 10-minute limit, we have what was equivalent to the emergency power before. So now you can kind of appreciate what these numbers represent. That's quite a difference in shaft horsepower on these engines. Now, as we talk about the major sections, we're not going to complicate this, gentlemen. Engines are engines are engines are engines. We're primarily going to talk about 4 major sections: inlet, compressor, combustion, exhaust. Often referred to as what? Suck, squeeze, bang, blow. That's it. That's what we're going to talk about. We're not going to change anything. Does this engine do it different than some of the engines? Sure it does. But once you understand it, you're going to say, hey, okay, I can relate that to this. Engines are engines are engines. These are just more powerful engines. Bigger engines. And we'll give you a good appreciation. Now, what we're also going to talk about is stations. When we talk about the stations, why do we have to reference stations? Why do you care about stations? Why do you care about stations on the aircraft? What does it help you do, gentlemen? Locate things. That's the simple gist of it. If I refer to terminology, i.e. T1, it would be neat to understand, where does T1 come from? Why do we reference T1? And it all has to do with these station numbers. Just like the aircraft itself, the engine's broken down into stations to help you identify locations, help you identify where the pieces and parts are. So you got station 1 right here. You got station 1 right here. You got station 2 starting right there, and you can see that station 2 is going to come all the way back to right here. And then this is where station 3 comes into place. And station 3 is inside of here. And you'll see why we have to reference that here in just a second. And then you got station 4. And then, of course, the exhaust being station 5. Why is it important to understand stations? Because we refer to things like P3. P being what? Simply pressure. That's all P is. P3, base being pressure at station 3. So we know that it's going to be right here. And we're going to talk about a lot of things on P3. Now they reference up here T4.5. Translation, what do you think or excuse me, T4.5 is?
Turbine bearing 4 point.
It's going to be your power turbine inlet temperature system. In other words, that's your PTIT indicating system. That's where it's at. And then one that we could throw up here is inside this inlet, we have T1 that we will refer to. Not only are we going to refer to it, you can see T1. You can actually see T1. And what it is quite simply nothing more than a probe sticking in there measuring the inlet air temperature. It's a probe sticking in right here, right there, measuring the inlet air temperature. So that's why we'll reference these different pieces and parts. Can you see better now?
Yeah.
I should have taken it off to begin with, see? There's a reason for everything. And like I said, you can see 832 pounds. And before, just so you know, I used to say the same thing about that, and then my wonderful students, being as great as you all are, would point out, come on, Tom, half the engine's missing. Now, I can say 832 pounds, and everybody can say, yep, okay. There you go. Any questions about that? As we look at the inlet section, the inlet section is going to comprise of a one-piece aluminum housing. This is that one-piece aluminum housing right here. That's what this is all going to consist of. Okay? Connected to it, it's going to contain your oil supply. Oil supply being right inside of here. And we will actually look at the other engine so that you can see it. We do have it open. And then it has the mounting pads for the following. The starter located at 12 o'clock position. We'll actually show it to you here in just a second. The oil filter, the torque junction box, and the oil level indicator. What are we talking about? In just a little bit, we'll show you the pieces and parts. But also back here, as part of that section, you're going to see a series of tubes and nozzles. The other thing that they made better for the 714 is the engine wash capability. Why? We used to pull that engine inlet apart, and we used to use some type of mechanism to spray that soap water solution in there. Well, what do you think would happen from time to time? And they would smack blades, and then they would damage part of the compressor section. By coming up with an engine wash system, it improved and it lessened the possibility of doing any type of damage because of pulling those inlet screens off. But, there's always a but, right? It added additional pieces and parts that, guess what? You're going to be responsible for being able to identify. And we'll talk about them all as we go along. There's your starter assembly located at 12 o'clock position. We are going to tell you a little bit more about it today than what you got yesterday. You got the most of the gist yesterday because it's a hydraulic motor. That's what it is. Part of the utility hydraulic system. And there's a close-up of it. You have the torque meter junction box. That's part of your torque measuring system. Now, this is also a good time to tell you that the right side of the engine is the right side of the engine. The left side of the engine is the left side of the engine. Meaning what? Meaning no matter whether it's the number 1 or number 2, the left side of the engine is always identified as the left side of the engine. It doesn't change based on whether it's the number 1 engine or number 2 engine, which means what? Which means from the left side of the aircraft, you're going to be looking at the left side of the engine. From the right side of the aircraft, you're going to be looking at the right side of the engine. Guess what, gentlemen? That's good cardinal knowledge, because if they climb you up on the right-hand side of the aircraft, guess what the questions are going to be about? The right side of the engine. So you can kind of get into the mindset, okay, what's on the right side of the engine? And then you pretty much know where they're going to take you discussion-wise. And part of it is your torque metering junction box, located right here. There it is right there. Okay? There's your torque measuring junction box right there. And there's a close-up of it. Now, it's right next to an inline fuel filter button, or inline fuel filter. That's going to be a good reference point. Why? Anything that has differential pressure indicators, you should be able to identify, right? That's part of your pre-flight requirements, to check and make sure all those buttons are in. So if I know that that's there and I got to look at that button, it's easy to kind of say, note what's around it as I'm looking at it. Accessory gearbox. Again, to me, this is the heart and soul. If you can identify the accessory gearbox 10 out of 10 times, there's nothing you can't be taught. There's nothing you can't find. There's very few things that you will be asked that's not associated with that accessory gearbox. There's your engine-driven fuel pump. Your engine-driven fuel pump is going to be driven off of what? The N1 off the accessory gearbox. That's what I'm talking about. And the fuel pump is easy to identify because of what fact? What do we know about anything related to fuel on aircrafts?
Fuel lines.
What?
Fuel lines.
Okay, but what about those fuel lines?
They're marked.
They are highly marked. Why? Why are fuel lines one of the most marked lines on this aircraft?
Flammable.
Okay. Zero tolerance for leaks, seeps, or any of the other normal words that you hear associated with that. So that's why fuel lines are so well marked. And that's one of the things you got to get into the mindset. You know, what advantages do I have to help me learn this aircraft? Well, I know that fuel lines are one of the most marked lines on the entire aircraft. For what benefit? To what purpose? And that purpose is ease of identification. Why? Because there's no leaks, seeps, or anything tolerated in fuel. So if I can find fuel, 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 all marked all over the line, all I have to do is follow it, and there's my engine-driven fuel pump. Why is that important? Because right behind it is going to be your oil pump. So if I can identify my fuel pump, then I should be able to identify my oil pump, and then behind it is an N1 speed sensor. So you'll notice it says your oil pump and a gas producing speed sensor. And again, all we're doing right now is talking about pre-flight and being able to identify the pieces and parts. And then your engine oil fuel filter. And this one has it removed, but it would be installed right here. But again, it's a filter, and it's not only just a filter. What does it have that you know you're supposed to look at?
Independent bypass.
Okay, it has an independent bypass button. It's a differential pressure indicating system. Why is that important to know? Because later on, we're going to show you how that filter system works. And we always reference differential pressure indicator. But how many people actually understand what do they mean by differential pressure indicator? I'm not asking you to actually raise your hand. Okay? Some of you do, some of you don't. By the time we're done, actually this morning, you will know what do we mean by differential pressure indicators, because you're going to find out that that's what all our indicating systems are. They're differential pressure. They're actually measuring a difference in pressure between the two different sections inside that fuel filter, or in this case, a fuel filter housing. But it's going to be applicable to all filter housings. And then your oil temperature sensor. Your oil temperature sensor, located right here. Okay? Now, sensor because why? Sensor because it's sending a signal to a computer system. But I am going to do you a favor. And that favor is, later on, we're going to use a lot of different terms. And we use them already. You got them, all sorts of them, yesterday under utility hydraulics. And a lot of people don't have a good grasp of what we're talking about. But this is going to be applicable to a lot of different systems. Oil, fuel, and hydraulic. But I'm going to give you a series of definitions, and this is just purely a favor. And this is the first time that I kind of get to explain them. So therefore, what I'm going to recommend you do is somewhere where you can reference, because they're going to be applicable across the board. So don't just write them here. But what I'm going to do is I'm going to give you some good definitions to understand. So wherever you want to write them down, I'm going to recommend that you write these down. What I'm going to start off with is transducers and transmitters. Transducers and transmitters. Okay, and we've seen those already. And it's a term we just throw around and we expect everybody to kind of have a gist of it. And most people don't. So, transducers and transmitters. Transducers and transmitters are going to take a fluid pressure. Transducers and transmitters are going to take a fluid pressure, turn it into an electrical signal, and send it to a gauge. Now, whether it's a transmitter or transducer, you don't care. Reality is, you don't care. The problem is, in one place you can see it labeled as a transmitter, and another place you can see it labeled as a transducer. But whether it's a transmitter or transducer, the gist is the same. And that is, it's going to take a fluid pressure, turn it into an electrical signal, and send it to a gauge. Okay, next. We got bulbs and probes. Bulbs and probes. Bulbs and probes are going to take a fluid temperature, convert it to an electrical signal, and send it to a gauge. Bulbs and probes are going to take a fluid temperature, convert it to an electrical signal, and send it to a gauge. Now I'm going to give you one more piece of tidbit for the CH-47. If you determine that fluid is oil, that gauge, whether it's pressure or temperature, that gauge is in the cockpit. If you determine the fluid you are talking about is oil, that temperature or pressure gauge is going to be in the cockpit. If you determine that that fluid is hydraulic, it's going to the maintenance panel. Whether it's a pressure or temperature, if you determine that that fluid is hydraulic, it's going to the maintenance panel. And then, of course, fuel is going to the cockpit. And guess what? There's no exceptions to that rule. None. So if you determine that you're looking at a pressure transmitter and you determine that the fluid you're talking about is hydraulic, that's going to be a pressure reading located on the maintenance panel. If you determine that the bulb or probe is associated with oil, i.e., which is why I bring it up now, this is technically a temperature bulb. So what reading is it going to give me? It's going to give me a gauge. So where's that gauge going to be? In the cockpit. Does everybody see how that worked? Which is why I give you these definitions. Not to make IPs out of you, not to make maintenance test pilots out of you, but throughout your entire Army career, That is a good basis for learning any aircraft that you ever may be asked to learn. Any questions about that? So there's your temperature sensor. Now the only catch is that word sensor. Why sensor? Because the signal is also going to the computer. The signal is also going to the computer. And you'll notice we changed a lot of things to sensors to help you understand that the signals now are being processed through the computers. Self-sealing chip detector, located on the left side of the engine. And we actually now have the ability to actually show you one. And that chip detector is located right there. That's where your chip detector is. Okay? That chip detector is located right there. Now, where does the self-sealing piece come into it? We can actually pull that chip detector out without draining the oil. Hence, self-sealing. We'll talk more about the chip detectors as we go along. Hydromechanical metering assembly. Now you'll notice this engine is missing it. Okay? They're hard to get a hold of. There are a lot of extra ones right now, especially taking care of the war effort in both Afghanistan and Iraq. They're just not available for us to get a hold of. But the hydromechanical metering assembly, if it was mounted to this engine, would be mounted right here. Keeping in mind that the hydromechanical metering assembly is going to consist of the FPU, fuel pumping unit, and the hydromechanical metering unit, HMU. Those make up the HMA. Power turbine speed pickup, located right here. This is the new sensor. This is the new sensor. What is it measuring? It's measuring N2 speed. But what's it connected to, gentlemen? What? Okay, but now what I'm looking for. What's it actually mounted part of?
HMA?
Not the HMA. The accessory gearbox, which we said was what driven? N1. So now we have a contradictory in terms, don't we? But what you're going to find out is part of it is another shaft that's actually going to drive a mechanism from your N2, from your output shaft. And we'll actually show you the output shaft in just a little bit. Now, in line with the compressor section, the compressor section is going to consist of 7 stages of axial compression and a single centrifugal stage. Now we'll get into exactly what we're talking about in a little bit. But as you look at it, you've got 7 stages of axial compression and then 1 centrifugal stage, and we'll actually talk about exactly what that's doing for you as we go along. Oil flow programming valve. Oil flow programming valve located on the liquid-to-liquid cooler. And of course, we have to flip the engine around again. My favorite thing to do. This is how I get my PT. Not my power turbine, my physical training. Okay. So the oil flow programming valve is mounted to the back of your liquid-to-liquid cooler. Here it is. Gentlemen, here's your oil flow programming valve. Your liquid-to-liquid cooler, obviously, we said was right here. What 2 liquids are we going to be talking about? Fuel and oil. Fuel and oil. And then last but not least, our ignition exciter, located right here. Sometimes you see that radioactive symbol on it. Same thing, here it is. Overspeed solenoid valve. And see, here's the problem. A lot of these pieces and parts can be seen. So therefore, they can ask you about them. Here's your overspeed solenoid right here. Okay? You got your bleed band actuator. Here's the actuator itself. But then you got this silver band that goes all the way around the compressor, located or in line with your number 6 and 7 stages of axial compression. And we'll talk more about that here as we go along. And then, of course, your inline fuel filter. It's a fuel filter, but the big thing about it is it has one of those differential pressure indicators. Affectionately referred to as an LRB, little red button, impending bypass button. Same thing. All the names are applicable. It's okay. Huh?
Pop-outs.
Pop-outs. But as long as you understand that you need to check that. But it'll help you also identify, okay, if that's my inline fuel filter, oh, there's my liquid to liquid cooler. There's my exciter box. There's my junction box associated with my torque measuring system. And that's how you can just prepare yourself for the different sides of the engine. A lot of people complicate this stuff, but it doesn't have to be hard. And we're not going to keep it hard. All right. Now we'll flip this engine around again. By the way, this is the first time that we're seeing this engine. We just got this engine. Before, we did everything using the 712, and now we actually have a 714 engine. Now, this is actually a Lycoming 714 engine. Why is that important? When we go, and since we're going to do a difference class for 712s, you're going to notice the layout is the same with some minor exceptions, and we'll highlight the changes as we go along. But later on, when we do 712s, because a lot of people already know they're going to units with 714, there's a tendency to just want to flush the 712 information. But reality is, you can actually still benefit from that class. Why? Because the same processes that were happening in the 712 are happening in the 714. The only difference is, instead of you controlling them, a computer is going to be controlling them. That's the only differences. But the same things are occurring. The same processes are going on. And that's just something to kind of say, hey, okay, what am I going to get out of this that I can associate to what I do need to know? Because that's what everybody always worries about. What do I need to know? And you can get some benefits out of that class that is going to be relatable to here. Okay? So now, we got our main fuel filter. Here's our main fuel filter. What am I going to be looking for on pre-flight? Again, we have another differential pressure indicator. LRB, impending bypass, pop-outs. As long as you understand that button's going to pop out, we need to make sure that it's in. Again, the HMA would be right here, but we don't have one. And then your start fuel solenoid, which is right here. And again, right now, all we're doing this first part is identifying pieces and parts. We'll get into exactly how they work and what they do in just a little bit. Any questions about anything we've covered so far? All right. Now, one more thing that we're going to talk about. With the start fuel solenoid valve, that is now DECU controlled, digital electronic control unit. Why is that important to understand? Because later on, when we do talk about the differences between 712s and 714s, and we talk about the start process per se, what you're going to find out is in the 712, you control the entire start process. In the case of the 714, the DECU does, to include that start solenoid valve, which is going to control our start fuel. And the magic number is 10%. That's what it's looking for. And we will re-emphasize that again as we go along. You should now be on page 14. We're going to look at that combustor section of your engine and everything that lines up with the combustor section. I'm going to start off with the air diffuser. That air diffuser assembly is located right here. Here's that air diffuser assembly, and it goes all the way around the engine. Now, we'll actually get into what it does, and we'll actually see the inside of it in just a little bit, but it mounts to the rear of the compressor section and does the final internal guide vanes and directing of air where we need it to go for both compression and combustion. The combustor assembly itself. This is where the air-fuel mixture is going to be ignited, and now we're going to combust it, hence combustor section. And now what we're going to do is we're going to direct those hot air gases to where we need them to go. And inside of there, they're going to drive 2 gas-producing blades or wheels to do what? To make the compressor section, the N1 section, self-sustaining. And then that hot air gases are going to drive 2 power turbine wheels, resulting in driving a shaft that's going to drive an output shaft, which is eventually going to drive your engine transmissions. And that takes care of all of page 14, except for we'll actually get to see in that combustor section, you got your 2 gas producing wheels, which is going to provide and keep that compressor section turning, and it's using the same hot air gases that are eventually going to be used to drive your 2 power turbine wheels, which is going to drive a shaft that comes through to your output shaft through here. And this is your power turbine section of your engine, your N2 section. This is your gas producing section inside that combustor chamber. Down at the very bottom, you have your fuel flow divider located at the 6 o'clock position. And basically, it's using fuel pressure to basically provide for your primary fuel and your secondary fuel. And it is going to be proportional to your N1 speed. And that's what's going to drive or increase that pressure. And there's a close-up of it. And then, of course, your exhaust section where your tail cone's mounted. But also we have to talk about your mounting. Now, why do we have to talk about our mounting? As long as the engine's mounted, you should be happy, right? But if this engine's not mounted right, the vibration caused by the engine could result in damage to the fuselage. Plus, that aft mount is adjustable for the process of what? Why do we need that aft mount to be adjustable? What's the purpose of being adjustable? Think about it. What do we want it? We want that engine to be in line, right? If that engine's not in line with the whole drivetrain, it's going to put undue stress and strain on the drive shafting and the transmissions and the engine itself, and therefore it's going to cause a premature failure. It may not result in immediate failure, but it is going to reduce the length that the time's going to be provided for. Also, it adds a component. You're going to notice down just below the engine, you have this mounting bracket. Contrary to popular belief, it is a storage area for that aft mount. Why? Because that aft mount is adjusted specifically for that aircraft, that tail number. The other thing about it is, if should it become necessary to replace this aft mount, that's the nominal length for the mount. for that engine, for that aircraft. So that's the two purposes that it provides for. It's not a mountain for anything else that you'll hear. A lot of people try to pretend like it's mounting for additional antennas or something like that. All it is a storage area for that aft mount. Now, because the aft mount's adjustable, it also has a up and down arrow so that it's installed properly. So on pre-flight, you want to make sure that the up arrow is pointing up and not down. That would be a bad thing. Any questions about that? The drag strut itself. The big thing about the drag strut, if you look at the drag strut compared to the 712, this one is thinner. And it also has a 2-degree bend in it, which seems weird. If you were to take it and put it down, you'd swear somebody had stepped on it and bent it. But they didn't. It has a 2-degree bend to facilitate the lines and the mounting. Now, why were they able to go to a thinner drag brace? Because we got a lot less vibration from the old 712s. And we're going to find out how they improved the 714. We're not just going to sit here and say, yep, the 714 is a better engine. As we go along, you will see and have it highlighted what the improvement was and what the benefit was. But because we reduced the vibration, they were able to make this drag brace smaller. Why is that important? That they were able to make it smaller? Weight. Purely weight. We want to reduce and keep the weight as low as we can. That's why they went through the process. Once they made the engine better and reduced the amount of vibration caused, reduced the amount of stress and strain put on the mounting and the drag brace, therefore they were able to make it smaller, reducing the weight. And between both engines, that's significant. Learning step activity 2. Describe the major sections of the power plant. Again, now we're going to look at the engine inlet, the fairing itself. As we look at the engine inlet fairing, this is your engine inlet fairing right here. It mounts onto the front of that one-piece engine inlet housing. All the inlet does is it provides for the direction of the air into the engine. It also provides for mounting on the back for that engine wash system. That engine wash system is going to be mounted right here, which is going to consist of the tubing and 8 nozzles that are going to result in spraying of water soap solution inside the engine. And it has the T-lock mounts for that upper and lower engine inlet screens that you will see. We'll make reference to EAPS, the engine particle separators, but we're not really going to make a big deal because reality is when they are installed, they limit your ability to actually pre-flight the inside of the engine. They also reduce the requirements for pre-flighting the engine inlet. Why? Because although it's on a rail and we can slide it forward, for pre-flight they don't do that. So there's no pre-flight ramifications from it. So there's your tubing and the nozzles, but down on the deck, where is that? Where are we looking at right there? What we're looking at is if you stand on the tarmac with the engine work platform down, whether it's on the left side or right side is irrelevant. The location is identical. The location is going to be just above the work platform on the back side of the aircraft or towards the aft section of that work platform. You have these 2 plug-ins or quick disconnects for the purpose of the engine wash system. The one is going to be for fluid, whether it's a soap water solution or eventually water for just rinse is irrelevant. One is fluid and one is air. Now, why do I need to hook up air?
Purge the system.
Purge the system, which is one of the answers that people come up with. But reality is it doesn't have anything to do with purging of the system. What else? Drying the engine, which is the second one that a lot of people come up with, has nothing to do with drying the engine. Don't be afraid to come up with the wrong answers. Why? Because people do it out on the flight line. I want you to hear some of the answers that people come up with. Huh?
Air's so important, it probably might be a means by which the maintainers do leak checks, some sort of air.
No, sir. Never had that one come up, but it's a good point.
Forcing fluids through the engine.
Which is the other one that everybody comes up with, and no, it is not. In a way, that's the closest answer that anybody normally comes up with. Okay? It is not actually pushing that airflow through it. What it is actually used for is closing that bleed band actuator. Because what the bleed band actuator results is a band that opens up right here between the 6th and 7th stage. Well, if this band is open, when we go to do the engine wash, where's my water and soap solution going to stop? Right here. And all my water and soap solution is going to come out. But where do I need the water and soap solution to really get to?
Back on the road.
I need it back here in the combustor section. The compressor section stays relatively clean. Why? Because we sandblast it. Dirt and debris, although we're sucking it up, is going to result in that kind of a sand wash, sand bath. Okay? So the compressor section is going to stay relatively clean. But what we need that water and soap solution to get to is this combustor section. That's what we need to clean up. And if that bleed band doesn't close, then it's not going to get back here. And so that's what that air is doing for us. It's just strictly closing that bleed band actuator.
What kind of pressure closes that bleed band?
You know what? I don't remember. They now have a wonderful engine washing cart. And it's got your water and soap solution. It's got your pump for pumping that fluid up. And then it's got a compressor that's going to be used and it's going to be plugged right up to the aircraft. And I don't know what it actually is now. Screens themselves, as we look at the screens, again, all we're doing is using the cowlings to actually protect the engine. That's all we're doing. Protecting it from being hit, damaged, kind of hiding pieces and parts so that people deciding to take pop shots, you know, can't just hit any piece and part on there. So that's part of the cowling. Plus it makes it self-containing for later on when we talk about the firefighting capabilities of the engine. It keeps that firefighting capability right around the engine where we need it the most. So it's going to be part of that. Of course, the engine inlet screens. I don't like FOD screens. FOD screens to me is a bad name. FOD stands for foreign object damage. Okay? We're trying to prevent that damage. So these are inlet screens. And when you look at the engine inlet screens, it's going to be primarily two pieces that you're concerned about, with the additional two more pieces that you also have reference to in your Dash 10, because they have to be removed anytime you're operating in temperatures plus 4 degrees and below. And those are called your bypass panels. And we'll show you what those look like. Now, these are the T-locks that we already kind of showed you when I pulled that up here. And the T-lock mechanism is used to hold the upper and lower engine inlet screens to that cowling. But here's the problem that you need to be aware of. On pre-flight, you need to take special precautions to look at them. Because if they're not adjusted right, they will vibrate out of there. And sometimes they're real easy to close. Other times you may have to pull the bypass screens off to close them, which becomes time consuming in some cases. At the very bottom cowling of the engine inlet screen is the ability to have access so that you can look inside the first set of compressor blades. reality is, even if you look in there, gentlemen, most of you are not sure what you're looking for. Okay? The other thing is, even if I identify damage to a compressor blade, you don't know if that damage is within tolerance or out of tolerance. So the most you can do is identify it, write it up, and then QC is going to have to come out and say, yes, it's in tolerance, or no, it's not in tolerance. And then the other thing that you'll see a lot or hear referenced, oh yeah, we know about that one, sir. Okay, because we do. We keep track of our engine inlet screens and our engine inlets, and we can pretty much, on my aircraft, I knew which compressor blades had damage and which ones didn't. I already knew which ones were checked out and which ones weren't. So you may also see that. Oh yes, sir, ma'am, we know about that one. And then the other thing is, you have to be able to reach in here, and you want to make sure that it's free turning. Why do you want to make sure that it's free turning, especially in colder temperatures? You want to make sure that condensation didn't form inside the engine over time, resulting in moisture which froze, and now that compressor section will not turn. And if it won't turn, you will damage those compressor blades. So you have to make sure that it's free to turn. There's the bypass panels, upper and lower. And again, they are supposed to be removed anytime you're operating in temperatures plus 4 degrees and below. The problem is, if it's clear blue and 22 and we're sitting on the ground, but we know we're going to fly to altitude, and we know we're going to be operating in temperatures plus 4 degrees and below, then they have to be removed. But the problem is not removing them. They come off relatively easy, relatively quickly. The problem is, some people can install them in a minute. Some people, it takes a lot longer, based on the fact that those nut plates with the vibration of the engines shift in there. So even though they come off relatively easy, sometimes lining them back up is a pain. Now, the problem is, what had happened is when you first look at the engine inlet screens, and you can actually see it, you can tell the screens used to be one size, which were pretty good sized squares. But the problem was they were still ingesting dirt and debris, which was resulting in compressor damage. So what they did is they came out with the modification, and all it was another screen, and you can actually see it mounted on top of the old one. And what it did is it just made these holes a lot smaller. But in making those holes a lot smaller, they made it so that one single drop of moisture can block anywhere from 4 to 5 holes at a time. So therefore, it becomes very, very important to remove those bypass screens, so if they should encounter enough moisture and it freezes and blocks a good portion of the holes, the airflow will still be able to get into the engine, not suffocating the engine, not resulting in flame out. Any questions about that? And the bypass screens are the size of the original screens. They didn't modify the bypass screens. They just modified the front ones. Okay, nacelle. We pretty much already talked about that. Serves as a protection for the engine. All right. Page 19 is where you should be. We're going to talk about the T1 sensor. Here's your T1 sensor, measuring the temperature of the air actually coming inside the engine inlet screen going to the engine. Okay. There's your T1 sensor right here. It's nothing more than a probe that sticks into the engine. That signal is going to go to the DECU, the Digital Electronic Control Unit. And what it's going to use that signal for is to determine what your N1 speed should be. That's what it's going to do. And we'll show you that here in just a second. We'll actually break them down for you. And it's located at 10 o'clock. We already talked about that. And we already talked about what it does. Okay, the accessory drive. Again, to me, if you can identify the accessory gear drive 10 out of 10 times, there's nothing you can't learn. So here's the accessory gear drive. And what you're going to notice is it goes the entire bottom of the engine. Here's the accessory gearbox. It is driven via the N1 system of the engine. As we look at it, and we'll actually show it to you here, there's the accessory gearbox, and it mounts down at the very bottom of the engine. It's going to be driven via a shaft driving or being driven by the N1 section of the engine, whether it's being sustained by the engine-driven hydraulic motor, the utility hydraulic starter motor, or the engine becomes self-sustaining. As long as that compressor section's turning, it's going to drive the shaft, which is going to turn the accessory gearbox. Mounted to the accessory gearbox is going to be your engine-driven fuel pump. And you know where it's mounted. It's mounted on the left side of the engine. Again, the engine-driven fuel pump can be identified by its marked. The engine-driven fuel pump will sustain the engine as long as you're below 6,000 feet. And it'll do it just fine. Next is the oil pump, which is N1 driven. It's going to provide, as long as that compressor section, the N1 section is driving, it's going to provide the oil that this engine requires. And it will be pumped to where it needs to be pumped. It has the ability to hook the HMA to it. And when we talk about the HMA, it's actually going to be connected to the fuel pumping unit of the HMA. That's what's actually mounted. And you'll see that when we talk about that. And then you got your N2 pickup. Your N2 pickup is right here. You got an N2A and an N2B, and we'll reference that in a little bit. But basically, N2A is going to go to the primary mode of operation for N2 speed. N2B is going to go to the revisionary mode. And we'll actually show you that. But what we want you to understand is here's that bevel gear right here that's actually providing for that N2 speed sensor. And it's actually driven via a shaft that's connected to the output shaft of the engine. And we'll actually show you the output shaft here in just a second. Compressor halves. As we look at the compressor halves, here's the one for that engine right there, for that 712. But it'll give us a good ability to reference some of the changes and some of the improvements that were made between the 712s and 714. As we look at the compressor halves, they give the strength between the engine inlet and that combustor section. These compressor halves is what provides that strength. We can remove one half at a time. We cannot ever remove both halves simultaneously. The engine will collapse in on itself. As we look at them, they're going to consist of your stator vane, guide vanes. Same thing. Stator vane, guide vanes do the same thing. Reality is they do a dual function, and we'll talk about that dual function. We'll talk about the bearing halves in just a second, or the bearings, as we go along. Now, as we look at them, these are your stator vane, guide vanes. These are the ones that belong to the 712, which is going to give us the ability to show you the improvements between the 712s and 714s. What you're going to find out is when we came out with the 714, they improved the stator vane, guide vanes. First off, stator vane, guide vanes. What is the purpose of the stator vane, guide vanes? It actually serves a dual purpose. One, it guides the airflow over the next set of compression. Agreed? Hence, guide vanes. But it also has the job of stabilizing the airflow as it comes off that first set of compressor blades or the previous set of compressor blades. Keeping in mind those compressor blades are turning in here. As it's gripping that mouthful of air, as it comes off the very tail of the fins of the blades, what's going to happen to the airflow? It's going to want to swirl. And then we would send swirling air over the next set of compression. That wouldn't be very good, would it? So the stator vane guide vanes are not only guiding the airflow throughout the compressor section, it's also stabilizing that airflow prior to entering the next set of compression. Any questions about that? Now, here's the other improvement. As you look at this stator vanes, guide vanes, what you're going to notice in here is these have a thin piece of metal on either side. Mounted to that thin piece of metal was a lead seal. Why lead? Because if it did chip, it's a soft enough metal that the engine would just ingest it, spit it out, and it'd be done, right? But as these chips away, what happened to the airflow going over the next set of compression? We would lose some of the effectiveness, right? So here's what they did. This first set of compressor blades, stator vanes, guide vanes, what you're going to notice is it has a lead seal. But that lead seal goes all the way across. Everybody see that? There's that lead seal. Now, what was the improvement? What you're also going to find out is these seals are going to match up with your compressor rotor. The compressor rotor on the old 712 was flat. But what you're going to find out, and we're going to actually show it, the compressor rotor for the 714 actually has grooves. And what's going to happen is those grooves are actually going to cut its own path in these seals. So the first few times that they run the engine, it's actually cutting its path in these seals for the purpose of what? For the purpose of transference, efficiency of the transference of air from one set of compressor blades to the next set. Good? Okay? So there's the first set. The next three sets are going to be a rubber abradable seal. Now, what's the first concern when we say the next three blades are a rubber abradable seal? What's the concern?
Rubber melts.
Rubber melts. And when we think of engines, we think of hot engines, don't we? But we have to remember, what is the front of the engine? What portion of the engine is it? Okay, but what else? It's the cool end, right? It's where the airflow's first coming in. So why rubber? Because rubber, it's still going to cut grooves into it, but again, it makes that tight seal to ensure the most transference of airflow from one set of compressor blades to the next set. Good? And then we're going to go back to a lead seal. Why do I want to go back to a lead seal?
Because it seals that bump up against the hot section.
Okay, now we're getting closer to the hot section of the engine again. So now heat does become a concern. But what else? What happens as I compress air?
It becomes warmer.
The air gets warmer as we compress it.
But lead melts as well.
But very, very high temperatures. Way below the temperatures we're talking about in that engine inlet. Keep in mind, when we talk about the airflow that we're sucking in through the engine, as we're talking about that airflow, the primary consideration is what? When we think about the airflow, what is our primary mindset? What's going to happen in here?
Combustion?
Combustion, that's our main mindset. But we also have to remember that we're using that airflow not only for combustion, but we're using it to cool the engine. Exactly.
80%.
Okay? Which is a good thing to keep in mind, because how were they able to improve, and what was the benefit from maximizing the airflow getting through the compressor section? It's going to give us the max cooling capabilities of that airflow, as well as combustion. Any questions about that? Now we're going to look at the bleed band. Why do we have to talk about the bleed band? Because in actual fact, in making that compressor section more efficient, we increase the possibility of what risk? Okay, resulting in compressor stall, which is the worst case scenario, which is what everybody focuses on. Okay, compressor stall being the worst case scenario. But what else do we have to keep in mind with this aircraft? Just as important in this aircraft is what? Requesting a power demand and the engine not being able to meet up with that power demand. Here we are, we're flying a 49,000 pound aircraft, and all of a sudden we've got to get over a hill. When I pull in that power, I want that aircraft to give me the power, and I want it now. I don't want it to have to think about it. I don't want a delayed reaction. Agreed? So one of the things they improved on was the bleed band system. Quite simply, by what they did, in here, you'll notice these are round, oblong, or oval-shaped inlets. Look at how big they are up there. Now we got these big, massive squares. Why? Because when that bleed band opens, we want to make sure that that airflow can get out as efficiently as possible. Ensuring what? Ensuring that we don't have compressor stall. Now the next thing that a lot of people don't understand is some people have a problem with understanding why is there a risk of compressor stall. And what I refer to it as is the funnel effect. That's how I refer to it. We got this big mouth, and then we got that little bitty teeny hole, right? If I take a liquid and I pour it in there at a nice steady pace, it comes in the big mouth and it goes out the little hole. No problem, no foul, right? Perfect. But what happens if I take that pitcher and I pour it out or dump it out as fast as I can? As a result, that mouth is going to fill up, and because that little opening can't keep up with the demand of the inlet, something's going to have to result. And what is that? And that is that fluid's going to back up still. Either doing one of two things. Either one, just not giving you the power as you're demanding it, slowing it down. Or two, worst case scenario, there's going to be sufficient backwash that's going to result in a compressor stall. Any questions about that? All right. Now, the actuator itself, located on the right side of the engine, is the actuator itself. And we'll flip this thing around so that you can see the actuator. There's the inlet. Excuse me, that's the main fuel. Forgot I had the engine around more than I thought. Okay. Here's your pneumatic actuator. This is your bleed band actuator right here. It's connected to a band that encompasses the entire compressor section between the 6th and 7th stage of axial compression. The actuator itself is pneumatic, gentlemen, meaning what? What does it use to open and close? Air, as we already discussed under the engine wash system. It uses air. But what you're going to find out is based on the mode of operation. What do we mean by mode of operation? Primary and revisionary. It's going to use two different mediums to produce that airflow, or that air for opening and closing that actuator. In primary mode, what you're going to find out is it uses P3 air directly. What type of actuator is it? It's pneumatic. So it uses P3. What was P3?
Pressure.
Pressure from where?
From stage 3.
From stage 3. So if we follow the line, what you're going to find out is it's going to get P3 air from over here, and we'll show it to you here in just a second. Okay, when I turn the engine back around. Now, why is that important? Because what it did, by changing the medium that it uses, what it did is it allowed for quicker response to those power changes. Meaning what? Meaning the old system, what used to happen is it used to use fuel pressure as a medium. And what you're going to find out if you look under revisionary, guess what revisionary uses as a medium? Fuel pressure. Okay, so in primary mode, it uses air coming from P3 air. In revisionary, it uses this fuel as a medium. But what happened was, by using fuel as a medium, what used to happen is the bleed band actuator, now it didn't really do this, but in theory this is how it seemed, is when I made a power change, what would happen is the engine would go, the pilots want me to open. And it would open ever so slowly. The pilots want me to close. Why? Because it had to take that fuel pressure as a medium and convert it into air to actually open and close that actuator, which was time consuming and it was slow. Good? Now what happens under primary, because it uses air, what happens is when you say that you want power, that system goes open, close, open, close. So you got a lot more quicker response from it because it was a pneumatic actuator and it's using P3 air. So there's no conversion that has to occur, which means it's a lot faster, which means if I've got that mountain in front of me and I pull in that power to get 49,000 plus pounds of weight over it, it's going to give it to me. Now, in revisionary mode, there's a phenomenon that's created because of that slow to open, slow to close possibility, or what we refer to is it not opening and closing according to schedule. Okay, you're going to see between 81 and 86 is when it's supposed to transfer from open to close and close to open. When you get into that power setting is when that's supposed to happen. Yes, sir?
Why is there such a delay in the reversionary mode with the fuel?
Okay, good question. Because what's going to happen is through the HMU, what's going to happen in this mechanism is it's going to use fuel pressure that has to be converted into what? Has to be converted into air, because that's what's going to actually open and close this valve. it's still using air to open and close. But now it has to go through the HMU as fuel pressure and be converted into a pneumatic system to open and close. And that's a little bit of a time delay. Now, did these engines perform just fine? Sure, these engines performed just fine for a long time. Okay. But we could get into, based on it not opening and closing according to schedule, one, we could get into a phenomenon called bleed band popping. Okay? What happens is that when it gets caught up into that middle area, what will actually happen is that band will open and close. But now here's the thing. When we used to get into bleed band popping, we knew it. How did we know it? It was noisy as all get out. You could hear it from the front of the aircraft to the back of the aircraft. You knew when we were having bleed band popping, and so did everybody else. Okay? You could hear it from miles away. Now, the problem is, bleed band popping was first identified by the popping sound that was created via that actuator not open, being fully open or closed in that intermediate where it was kind of forcing the air through, but it was still closed, which was resulting in that popping sound. But the problem is, what do we have today that kind of cripples us from being able to identify that? How many people have CEPs? What's the purpose of a CEP? Cut out those additional sounds and outer noises, and it allows you to hear the radios and the intercom system a lot better through the hearing protection. So it keeps the outer sounds out and just allows you to hear the radios and the intercoms. But the problem is, that was one of our assets for identifying especially engine problems. If that engine quit, you'd hear the sound difference long before you caught it on instruments. Okay? Bleed band popping was the same way. So now that we've taken one of our avenues away, now we have to be more in tune to what instrument indications am I going to get in response to the bleed band popping. Torque fluctuations. But here's the problem. With torque fluctuations, sometimes they're so minor you may not realize it right away. Which is why, what's going to be probably your more drastic indication? PTIT. Now, how could I relate it to PTIT? What is the mindset that we normally think about that combustion, but we forget about the fact that we're using that airflow also to cool. So our PTIT fluctuations may be greater than our torque fluctuations in a lot of cases. Because why? Because we're not only using that air for combustion, but we're using that air as a cooling medium. And if we're reducing the efficiency of the airflow to get to the combustor section, we're also going to be running hotter temperatures. Which is why you may see those more drastically than you'll even notice torque fluctuations. Any questions about that? Okay. And it reduces, and we already talked about that. Now we're going to look at our compressor blades and our compressor rotor. Now, as we look at our compressor blades, the first thing that a lot of people notice, and we actually got rid of our compressor half, it's up at Fort Campbell being cut, but when they looked at these blades and they look at those blades seem shinier than the blades that we're looking at on this engine. But what you have to keep in mind is this engine's been ran a lot longer than this engine right there. Why? Because 714s are a fairly new engine. Over a period of time, those blades are going to look like these blades. Now, why is that important to understand? Because people think there's a material difference. They're both stainless steel blades. But what you're going to find out is those are a higher caliber of stainless steel. But they're both stainless steel blades. A lot of people are under the impression that those are aluminum. They're not aluminum. They're stainless steel. Any questions about that? Any questions about anything we've been covering? Then we're talking about the compressor rotor assembly now. In looking at the compressor section, we have 7 stages of axial compression with a single centrifugal stage of compression. And what you're going to notice, remember that blue slide, and I said we were going to cover all the information eventually as it comes along? You'll see under the one single stage of centrifugal compression, you're talking 9/32 to 1 ratio, just for those that are curious. Okay? Now, as we look at the compressor rotor, again, we've got our compressor blades. The compressor blades we already talked about are made out of stainless steel. The things about the compressor blades, we can actually replace the compressor blades. Our back shop can actually do that. But if they replace one, they have to replace the other one 180 out from it to keep the weight in line and in tune. If it's out of weight tolerance, it'll cause a uneven, and it'll cause it to vibrate and cause stress and strain. And it has a very, very close tolerance in there. Now, the other improvement was the compressor rotor itself. And this is the compressor rotor, gentlemen, right here. This is what the blades actually mount to. But you'll notice that we have the grooves. And you can actually see how those grooves, and they will actually cut their own path into the lead and rubber seals. Doing what? Ensuring the max transference of airflow from one compressor section to the other compressor section, or the one set of compressor blades to the next set of compressor blades throughout this system. Why? So we can get the max airflow to that combustor chamber, not only for combustion, but also for the cooling process. Now, as we look at the compressor rotor itself, the bearing packages that support the compressor rotor are the number 1 and number 2 bearings. Now, here's the problem, gentlemen. You're going to find out that there are 7 bearing packages in this engine. But the tendency is to go 1, 2, 3, 4, 5, 6, 7. And the bearing numbers don't follow that path. What they follow is the airflow path. Meaning what? Meaning it does the N1 section, and then it does the N2 section. When we talk about the N1 section, we're talking about that compressor rotor and compressor section. So you got bearing package number 1 right here, and bearing package number 2. Now, why do you as pilots care about bearing packages? That sounds like maintenance to me, doesn't it?
Because an IP is going to ask me.
Yes, but why are they going to ask you? Why do the IPs care that you know what bearing packages are?
Pre-plated, fine inside one of the case drain tubes or something, oil laying in there, residual might be coming from a specific bearing.
Okay, what else? Why else the importance of being able to identify, and probably more important than anything else, the different bearing packages? What is your Bible per se? The dash 10. And guess what they reference in the dash 10? They reference the different bearing packages. Why? Because some of the bearing packages are connected to components that you have to be able to identify. Okay? Some of those components are connected to gauges, which you have to be able to identify. And then last but not least, some of those bearing packages result in applied limitations that you have to be aware of. And that's why you have to be able to identify the bearing packages. You're going to find out that that number 2 bearing package is very important. Even though it's inside the engine, even though it seems like it's hidden, It's very important for two reasons. One, what type of bearing package is it? Where's it located? What?
Carbon bearing, isn't
Say that again.
it? Carbon bearing, isn't it?
Okay, but not what I'm looking for.
Ball bearing,
Not what I'm looking for.
diffuser,
It's in the hot end of your engine. So therefore what? It's going to have some special requirements. Because why? In the hot end of the engine, it's going to be more fair wear and tear. Agreed? The other thing you're going to find out, the other reason why that bearing package is referenced so much, is you're going to find out that your oil transducer is sharing a reading coming off that bearing package, or sharing the same oil supply going to that bearing package. So that's where that transmitter is picking up its signal. Okay, what do I know about a transmitter?
Goes to the gauge.
It goes to the gauge. What gauge? Where?
In the cockpit.
In the cockpit. Because why? How did you deduce that?
Just we talked
It
about
was
that.
oil, it was a transmitter.
There you go. Because it's a transmitter, because it's oil, we know the gauge is in the cockpit. So that's why the number 2 bearing package becomes a big deal. In the bearing package, the number 1 is going to support the front end of that compressor rotor, and that number 2 bearing package is going to support the back end of that compressor rotor. Any questions about that? Now, rotation for the N1 is going to be the opposite direction of the N2. So what you have is you have your compressor blades turning one way, but keep in mind that in the combustor we have a set of compressor blades for the purpose of what? Self-sustaining the engine. Everybody is afraid to answer, but all the compressor blades in the combustor section are doing is because they're driven by the same hot air gases as the power turbine wheels, is that's what makes and provides for the self-sustaining capability of the engine. Because eventually we're going to turn off the hydraulic starter, and when we do, something still needs to sustain that compressor section, and that's what does it. Now, as we look at the air diffuser, here's your air diffuser assembly. And again, why is this so important? Because we're going to reference a lot of things off of it. We got 2 oil taps. Why do we have 2 oil taps? One for oil in and one for oil out. But also part of the diffuser is the reference to P3 air. And what you're going to find out is you have 2 P3 air taps. Why 2? One's going to go to your HMA, the HMU portion of the HMA, and the other one is going to go directly to what? The bleed band actuator. So that's why you have to be able to identify those different taps. Any questions about that? Now, the P3 air that goes to the HMU is also going to go to the DECU, the Digital Electronic Control Unit. Why does it have to go to the DECU? What interaction is it going to have based on that P3 air pressure? What's it going to be used to control? What do you mean fuel, sir? Why fuel in relationship to what? What's it going to be doing?
power and demand,
What?
power and demand.
Not what I'm exactly looking for. What's it going to do with the relationship with the fuel? It has to adjust the air-fuel mixture for either leaning it or lean or, huh? Enrich the air-fuel mixture for the process of what? Making sure that engine sustains the right proper speeds. Any questions about that? So that's why it has to have that P3 air tap. All right. As we continue on looking at the combustor chamber housing, what you're going to find out is the air diffuser is then actually going to mount to your combustor chamber right here. Here's your combustor chamber. As you look inside that combustor chamber, it's going to consist of the following, and we're just going to run through them. You have your, and it's just going to start with your vane assembly. As we look at your vane assembly, for the purpose of what? All that vane assembly does, and here it is, it's going to take that final compressed air and it's going to do what? It's going to direct it into that combustor chamber in the direction that we need it to go. So all it's doing is guiding it in there. And you can look at that. It's just mounted inside that, inside of here. It's mounted inside of here, and that's what's providing for the direction of the air. From there, it's going to go to that liner assembly. Okay? Here's the liner right here. And what you'll notice is that liner is actually going to form inside of here, but you'll notice two things. One, as the airflow comes on, what's going to, or comes into here, what are we going to use that airflow right here for? Cooling. It's going to form a nice little pillow of air helping with the cooling. Now make no beats about it, gentlemen. If you touch that combustor section, it is going to burn the crap out of you. Okay, it's still going to be hot, but it's not going to be as hot as it would if we didn't have that pillow of air. But second, you're going to notice that liner has a series of holes. For the purpose of what?
Maintaining the flame in the middle without touching.
Exactly. It's making it directional. It's going to keep that fire and those hot air gases where we need them to be. As well as it's going to start directing it to where we want those hot air gases to go. Now, as we look at the liner, you'll notice it has this white coating. Now, contrary to popular belief, that white coating is not there to help you identify the different sections of the engines for training purposes. It is actually a white coating in there. But what that white coating is a ceramic coating. And I don't think, nope, yes we do. I have the curl assembly. This is the curl assembly. This is this piece right here. And what you're going to see in this curl assembly is it has that ceramic coating. And all that ceramic coating does is provide for what?
Protection.
Protection from
Metal failure. Or the, well, I mean, it keeps, ceramics they dissipate in heat better than.
They dissipate heat better. They help with the controlling of the heat. That's all it does, which is why this engine is a lot more heat tolerant and can run hotter. Because they've done a lot of things to make and help with that process. To include maximizing the amount of air that's getting into that combustor chamber. How did they maximize it? By making the airflow from the front of the compressor section to the back of the compressor section more efficient. Any questions about that? The turbine section. As we talk about the turbine section, it has the curl assembly right here, which we already just passed around, and it actually causes that hot air gases with that airflow to be directed through. And Lycoming was always famous for this S configuration. Okay? What's the relevancy of understanding there's that S configuration there? What did it help do?
It also helps to slow down the air before it gets to the...
I don't know that we want to slow down the air. But by having that S configuration, it makes it so that these engines are smaller. They're not as wide as they could be if it was a straight inline process, which a lot of engines use. So by using this S configuration, it maximizes the air directional, as well as keeping that engine still smaller.
You lose power because of that S configuration.
Well, keep in mind, what is the difference between a thrust engine
It goes basically,
and our turbine engines?
it goes basically in a straight line. You have less space for a turbine engine, because most of the time they're like S configured and all that stuff. But for air to turn the opposite way, it costs a lot of energy. So
And we want to bleed off that energy. Keep in mind, we don't have thrust engines. Contrary to popular belief, these engines are not providing any thrust capability. Could we? Sure, these engines could. Matter of fact, there's out there, they modified these engines for the Ms. Budweiser, which did what? Those were thrust engines. All they did was modify these engines to provide for thrust. How did they modify it? They pulled out a diffuser section that's at the very back of this engine, which is used for reducing the thrust airflow coming out of there, because we don't need it. All we need it to do is provide for what? Drive. So what's going to happen is it's got that power turbine wheels that are going to result in driving a shaft, which is going to result in driving a transmission, which is going to result in driving our rotors, which is the way we need our engines to provide. So the S configuration isn't hurting that process at all. As a matter of fact, you're going to find out that they still maximized the potential for these engines, which is the other reason why our engines counter-rotate. Because what's happening is, not only are we counteracting torque in that engine, but by having them rotate the opposite direction, we're using the hot air gases coming off of our N1 section blades to actually accelerate our power turbine blades, so that the engine has its power, and it has more than enough power. Power wasn't our problem before. We've never been engine limited in this aircraft very often at all. Okay. So now as we look at it, the hot air gases are going to be now driving the two gas producing blades, which is going to result in, because they go the opposite direction, it's going to accelerate the power turbine blades, which is going to drive an integral shaft that's going to come forward. But now we need to talk about some more bearing packages. Bearing package number 3. Now it goes back in order again. So what did we do? We went bearing package number 1, bearing package number 2, and now we're coming back up here to bearing package number 3. But bearing package number 3 is the front support for the integral shaft. Here's your integral shaft, which is going to come back up through the engine. So that bearing package number 3 is actually the support for the front of this shaft. Good? And then bearing package 4 and 5 is going to be the support for the very back of the integral shaft. Keeping in mind, what reference to the 4 and 5 shaft do we have? I mean, 4 and 5 bearing do we have? What reference to the 4 and 5 bearing package do we have?
Reference, you mean the PTIT gauge or?
No, sir. What reference do we have in the dash 10 in association or concern with the number 4 and 5 bearing package? As it directly relates to you.
Torque.
Not torque. How about a time requirement between starting the number 1 and number 2 engine? Or the first engine you start and the second engine you start? What is that time requirement? 3 minutes. Within 3 minutes of starting the first engine. It's a concern for the number 4 and 5 bearing package. Why? There's no oil being pumped back there yet. Why?
Because
What?
They're working off the same oil supply, and the other engine will starve that engine.
No, it doesn't show the same oil supply. They're completely separate.
Is it backdrafting that engine?
Okay, here's the problem. Okay, and we're going to go into more detail about it under powertrain because it's actually part of the powertrain class. Inside that engine transmission is a sprag clutch. Okay? But what happens with that sprag clutch is it has enough residual contact in there that as a result of starting one engine, whether it's number 2 first and then number 1 or 1 or 2, it doesn't care. But the first engine you start is going to result in the drivetrain turning. As a result of the drivetrain turning, the other engine's N2 section is going to be turning. Because now what's going to happen, and I can do it right here, okay? I can actually do it on this engine, where before I couldn't do it. What I'm going to do is I'm going to turn this shaft, which is resulting in turning that integral shaft. But what you will notice is as I turn it, is that compressor section turning? Something's turning, and it's those 2 power turbine blades back here. But because the compressor section's not turning, what else is not turning? The oil pump, or the N1 section. But we were going to get to the oil pump. So therefore that number 4 and 5 bearing package is not being lubricated. Keeping in mind that 4 and 5 bearing package is what portion of the engine? It's a hot end portion. So that lubrication is very important. And you can see, although I'm turning the output shaft, which is resulting in the turning of the integral shaft, you can see that that compressor section is not turning. Any questions about that? Now, as we look at the gas producing section, it should be on page 28 of your handout. We're going to break down the different sections. So here we go. You got your gas producing nozzles. Now, what is the difference between nozzles and stator vane guide vanes? What are the differences between nozzles and stator vane guide vanes?
Well, guide vanes, the air strikes it and then it's redirected, where a nozzle is actually producing the air as it comes out.
And John has. Actual fact, nozzles, except for the fact that instead of 2 halves, like your stator vane guide vanes were, where are my stator vane guide vanes? Okay. If you look at your stator vane guide vanes, you're going to notice that these 2 halves just mount inside your compressor section. That's all they do. But what you're going to notice when you look at your set of, if you ever get a chance to look at your nozzles, although they form a complete circle, will actually consist of several pieces. The other thing associated with nozzles is some type of cooling process, where you have the ability for air to transfer through those to help keep them cool, which is the other thing. So as you look at it, here's your first set of nozzles. And then you have your first set of compressor blades associated with N1. And then your second gas producing nozzles. And then your second set of compressor blades. And then your power turbine nozzles, N2 nozzles, your first power turbine wheel, your next set of power turbine nozzles, which you're going to find out, there's your other nozzles. That is your gas producing, their second set of nozzles. That's what these are right here. Okay? And then you got your second power turbine wheel. So there's your second gas producing nozzles, your two gas producing discs. What you're going to notice about your gas producing discs, they have slits in them. All those slits are part of the cooling process. That's all they're part of. First power turbine nozzles, second power turbine nozzles, and then we go to your output shaft. Your output shaft would connect to right here. Here's your output shaft. Your output shaft connects to right there. There's your 6 and 7 bearing package right there. And just so we're all on the same sheet of music, there's your output shaft right there. There's your output shaft right there. Any questions about that? And your output shaft is going to be driven by the integral shaft via your N2 section of your engine. And then it's going to be connected via a quill shaft to your engine transmission, which is now going to drive the drivetrain and eventually up to the rotor. Any questions about that? And again, at the very front, you got your 6 and 7 bearing package right there. So bearing package 1, 2, back up to the front, 3 of the integral shaft, 4, 5, back portion of your integral shaft, 6, 7. And keeping in mind that once you go to the next section, it goes back in order again. So it'll be 6 and 7. Any questions about that? So there's your 6 and 7. And then we go into our exhausts. As we go into our exhaust, mounts to the rear of the engine, they are interchangeable, gentlemen. They are interchangeable between the left side and the right side. Now, why would that be important to understand? Because what you're going to find out, if you look at a 712 engine, those exhaust tail cones just come straight out the back. If you look at the 714, now everybody's going to go into the fact that it's a lot shinier. Yep. Why is it a lot shinier? It's newer. It'll change colors just like all of them. Okay. And then the next thing you're going to notice, besides the shininess, is what? It's tilted out and up. to take that hot air gases that come out of the exhaust away from the aft pylon. That's the process that's going on. Now, the next thing that will be pointed out to you is the new exhaust tail cones have these ribs right here. What is the purpose of these ribs? And everybody's like, psh, it structurally helps it. No, it has a specific purpose. It actually strengthens that tail cone for the process of what? That if this engine should eat itself up, all the pieces and parts are going to go straight out, and it just strengthened the tail cone, meaning that as it exploded or as the pieces and parts failed, they didn't go through the fuselage right there back in the back. So they actually strengthened the tail cone. Next thing you're going to notice are these standoffs, kind of referred to as the Frankenstein effect. You know, instead of the bolts in the neck, you got these standoffs. And what they are doing is supporting 4 bars that are going across, and all those bars do is support this inner tail cone. Now, contrary to popular belief, the only thing that inner tail cone is doing is stabilizing the airflow coming out of the exhaust. It's not part of any other processes. Okay? Now, do we have a cooling system out there? Yep. Is it installed on all our aircraft? Nope. Okay? This is not part of it. All this does is stabilize the airflow coming out of the tail cone. That's all it does. Any questions about that? Okay. And it does say that it reduces it a little bit. How does it reduce it? How does it reduce the temperature? Just accelerates it coming out of the tail cone. So as we look at it, now we're going to break it down and we're going to look at the airflow again. And all you're going to do is you're going to see the airflow as it comes in. It gets compressed. It forms a nice little cushion of air right here for the cooling process. It's going to come back here to the nozzles where the air-fuel mixture is now going to intermesh. You're going to find out you have 28 nozzles encircling this engine. For the purpose of what? Max efficiency of the air-fuel mixture spray going into that combustor section. That's all it does. Part of that airflow is then going to be routed in between and part of that liner to help again with the cooling process. It also helps again with the airflow direction, making sure those hot air gases go in the right direction that we want them to. Everybody see that? We have combustion, ignites it, burns it, and then the hot air gases are going to drive your power turbine, or your gas producing wheels, and then your power turbine wheels. And yes, it looks like a set's missing, but there are 2 power turbine wheels. Driving the integral shaft as it comes back through, then it connects to the output shaft, and then it's going to drive your transmission and eventually your rotor. The only other thing we're going to find out with this picture is we have 2 start fuel nozzles, one at the 9 o'clock position, one at the 6 o'clock position, and we have 4 igniters. Where are all the igniters? The cardinal positions, the 3, 6, 9, and 12 o'clock positions. Any questions about that? And again, there's the breakdown of all the bearings. Keeping in mind, bearing 1 and 2 supports the compressor section. 3, 4, and 5 support the integral shaft and the power turbine. And then 6 and 7 support the output shaft. The only other thing that we're going to take advantage of is keeping in mind the 2, 4, and 5 bearing package are classified as hot air bearings. The 1, 3, 6, and 7 are all cool bearings. Why would that be important to understand? The hot end bearings are going to have special requirements. Why? Because they take the most of the wear and tear. Now let's say 3. Describe the operational characteristics, functions, and limitations of the engine subsystems. First thing we're going to start off with is the N1 speed sensor. The N1 speed sensor, and I'm actually going to let you see on this engine, I'm actually going to show it to you from the left side. And why am I going to show it to you on the left side? Because there's a lot of wires and lines on the right side that are actually going to result in blocking it. It's actually mounted right here. This is where it would be. Good? Okay, now what I'm going to do, Bus, help me push this engine this way. It's actually not installed on there. 1, 2, 3. Thank you. So now what we're going to do is we're going to look at the other engine. Can you see it okay? Here's that N2 speed sensor right here, mounted to the back of the oil pump. Basically what's happening is the accessory gearbox is turning in conjunction with your compressor section, so the oil pump is proportional to the N1 speed. So on the back of it you have your N1 speed sensor. But what you need to keep in mind is this N1 speed sensor, 1, it's a magnetic speed sensor. 2, the only thing it is doing is sending a signal to your gauge in the cockpit. I'll say that again. The only thing this speed sensor is doing is sending a signal to your gauge up in the cockpit. Why is that important? Does the DECU, the digital electronic control unit, need to know what your N1 speed is?
Obviously not.
Huh?
Obviously not.
Actually, it does. But that's not the signal that it's processing. I'll say that again. That is not the signal that DECU, the digital electronic control units, are processing. The only thing that signal is doing is producing a signal that's going to go to the cockpit, the gauge up in the cockpit for your N1 speed. Now, an N1 overspeed exists when you exceed what? 110%. Keeping in mind that 712s and 714s are different. And while you're here at Mother Rucker, you are responsible for both of them. Are they finally getting rid of the 12s? Okay, are you getting rid of the 12 emergency procedures? Oh, good. Not for you all. That's what I was afraid of. Okay. They make one determination at AQC and another one at Flight School 21. They try to keep AQC away from 712 engines because most AQC people are going to 714 equipped units. Okay? But right now we don't have that luxury to guarantee that to Flight School 21. So that's where we're getting rid of it in one section, but we haven't gotten rid of it in another. Okay, so I do have to be careful. Okay, because there was for a long time there was confusion about this. Okay, people tried to make 712s and 714 N1 overspeeds identical. They're not identical. Okay, for 712 it's one speed, and since you all don't have to know it, I'm not going to beat you up about it. I'm not going to make a big deal about it. Okay, but it's one speed, where a 714 and N1 overspeed exists when you exceed 110%. Any questions about that? Now, when we talk about a magnetic pickup or a magnetic speed sensor, what we are talking about is the fact that it's using pulsating magnetic pulses to detect speed. What do we mean by that? You'll notice it just uses a magnet inside of here. And what happens is as these raised gear teeth align with the pole, that magnetic field is going to grow larger or incorporate it. And basically what's happening is that magnetic field's going like this, which is interpreted as a speed. That's the only thing that's happening. Why has this become such a big deal? One, this is a change from what we had before. We had a tach generator system before, meaning what? Meaning it actually created an electrical signal proportional to how fast that shaft was turning. Now it's actually using magnetic pulsating. The other reason why it's so important is because we have a lot more speed sensors on here using this system. You are actually going to see this process occurring 3 times. The final time that you see it, we will actually show you a video of how it works. And what you'll notice on the top of page 35 in a note, they actually have what this process and how this process works. But I'm not going to read it to you. You can read it on your own, and it's great information. Now, your indicating system. You do not control where your N1 speed is set. But what you are going to find out is the digital electronic control unit is going to control where your N1 speed is going to end up. The only thing you know is that you're looking for a minimum of 50% N1. But what you're going to notice is in order to get that minimum of 50% N1, you have to be at minus 54 degrees C. So how often at Mother Rucker do you think you're going to see 50%? You're not. Now, it tells you that you're looking for a minimum, but isn't it good to kind of understand the relationship between what you're seeing on the gauge and why it's doing it? And that's the only reason why we're going to highlight it. Basically, what the DECU, the Digital Electronic Control Unit, is setting your N1 speed based off of is temperature. And that temperature is coming from a sensor located where? Huh? The inlet. That's the T1 sensor right here. It's sending a signal to the Digital Electronic Control Unit, and it's adjusting that fuel flow going into the engine based on that temperature. But how is that going to be indicated to you? As an N1 speed. So based on the temperature for a standard day at plus 15 degrees, you're looking at approximately 55. So pretty much that's what you're seeing around here right now, give or take a little bit. Agreed? And then on a very hot day of 57 degrees, you're looking closer to 59%. So you're looking for 50 to 59%. Any questions about that? Okay, next thing we're going to talk about is your power turbine inlet temperature. Your power turbine inlet temperature is being measured via 10 thermocouples that encircle this engine. Here's what the thermocouples look like. And basically what you have is dissimilar metals. As those dissimilar metals heat up, they're going to cause continuity. Simple gist. Why? Because as the different metals expand differently, it's going to cause continuity. But what you're going to find out is we said we have how many of these couplers? 10. How many gauges do you have up in the cockpit? One for each engine, right? 2. 1 for each engine. What you're going to find out is those 10 thermocouplers are mounted right here. And they are completely encircling the combustor section of the engine, measuring the hot air gases as it comes off of those gas producing blades just prior, hence power turbine inlet temperature, measuring the hot air gases just before it goes to the first set of power turbine wheel. Now what you're going to find out is although we have 10 thermocouplers, it's going to go to what's called a PTIT bus bar. This is the bus bar. How does that affect you? What is your knowledge requirement? What's going to happen is that bus bar is going to take all 10 thermocouplers and take an average of all those readings, and that's what gets sent up to the cockpit. But here's the problem. Does it go just to the cockpit? No. It also goes to what now? The DECU. And what you're going to find out is it actually goes to the DECU, and then the DECU is going to send a signal up to the cockpit. Now, why does it have to go to the DECU? Why does it have to go to the DECU?
Well, you have to match your PTIT.
Exactly. It has the possibility of matching PTIT based on what, gentlemen? Load share switch. The load share switch. Say that 10 times over. Okay, I can switch it over to PTIT, and then it will match the output of those engines based on the PTIT indication. Any questions about that? Now, what else do we have to talk about? We talk about the fact that it goes to the DECU for the point of load share, but now we also said it goes to the gauge up in the cockpit. So the next thing we need to talk about is the PTIT ranges, which is the first thing that bothers everybody. Why does it bother everybody? Because there's no set pattern. It gives you a front range, in the case of a 714, from 400 to 815 degrees C. And then it goes to 30 minutes, but the only thing it gives you of that 30-minute range, per se, is what? The top of it. That's the only thing it gives you. So what will happen, what are we talking about range? It's actually going to be from 816 to 855. Well, if that's the top of that range, then it has to go one above. And we'll show you why it gets confusing here in just a second. The 10-minute range is going to be from 856 to 900. Now here's where it gets a little confusing. The next range that it gives me, as per the -10, is what? The contingency power for 2.5 minutes of 900 to 930 degrees C. Which now just throws everything off, right? Everybody wants to say that should be 901. Okay? Reality is, gentlemen, that 1 degree isn't going to make a bit of difference one way or another. What you're going to find out is it's going to go from one right into the other one relatively quickly. But everybody gets focused around this. Why? Because it's part of your EPs and limits test. But the nice thing about it is you have to know the 400 to 815. Then you have to know the 855. Then you have to know the 900. And then you need to know the 900 to 930 for 2.5 minutes. And we're going to talk about that one here in just a second. And then from 931, reality is all you needed was the 940, not to exceed, right? But from 930 to 940, you can be in that range for no longer than 12 seconds, keeping in mind that we have another chart associated with the start process only, which tells me that I can actually, during the start process, actually get into those ranges, can I? Not to exceed how long? 5 seconds. That's a whole different process. But keep in mind, the nice thing about the 714 is what controls this process. The DECU. The DECU, the Digital Electronic Control Unit, as part of the FADEC system. Okay? For the start process. And we'll talk about that entity in just a little bit. Okay? Right now, we're just trying to get the ranges. Never to exceed 940 degrees C. But what you're going to find out, we need to talk about contingency power, because where does the confusion come in? Let's go ahead and nip it in the bud. You ready? If I go into contingency power, I go into it for 2.2 minutes and I come out of it. Do I have a write-up? Nope. Any harm, any foul? Nope. I come right back into it. I'm in it for 2.2 minutes. I come right back out of it. Any harm, any foul? Any write-up? No. Okay. I come in for 2.3. I come back out of it. Any harm, any foul? Nope. Okay. I pull back into it. I'm in it for 2.2. I come back out of it. Any harm, any foul?
Depends on how low you go. Good.
What do you mean, sir?
She'll also at the 10-minute range.
Ah, here's what people forget, gentlemen. I still have to be concerned about that 10-minute range. If I don't go below 900 degrees and actually below 855, I could inadvertently forget how many times I went into it and out of it and get into the 10-minute limit if I'm not paying attention. But let's nip it in the bud. Contingency power is there for the purpose of what? Single engine operation, sustaining flight. If you need it, use it. If you don't need it, and if you can play around with it, chances are you don't need it, then stay the heck away from it. Okay? The next thing, yes, you have to know these times. But if I exceed any of those times, what happens to my aircraft, gentlemen? If I exceed any of those limits, I'm in contingency power for 2.9 minutes.
Just needs to be inspected before it flies.
All I have to do is inspect the hot end section of the engine. Why is that important? Because if I'm out over water and I need single engine, I need contingency power to get me to land, I'm not going to land in the water just because I exceeded that limitation. I'm going to go ahead and get it to where I need it to be, and then I'm going to put it down. And the problem was that everybody associated this with some type of automatic failure, or they thought the aircraft was going to turn into a pumpkin. All it does is it kicks it into a special inspection. Why is that important? So that if you can't land the aircraft, you don't have to play games with contingency power. If you need it, you need it. Use it. You land at the first place that you can land, and then you handle your business. What's going to happen is we're going to fly another engine out to you. We're going to pull that engine off. We're going to put the new engine up there, and then we'll probably get a one-time test flight back to Garrison. That's all that's going to happen. But if you don't have the right mindset, it's kind of easy to get confused. Questions? Moans, groans, gripes, complaints.